Hello everyone, our Python for Chemistry series. In our last couple of videos, we promised to dive into the world of iterables, and that's exactly what we're doing today. This is a fundamental concept in Python, and we'll start with one of the most common, the humble yet most powerful iterables in Python, the range object. What exactly is an iterable? Let's start with the basics. What is an iterable? Simply put, an iterable is not a data type itself, it's a property of an object. Think of it as a data collection that you can loop over, meaning you can go through its elements one at a time. You can also pass it to Python's built-in iter function. Python has many iterables: string, range object, our focus today, list, tuple, dictionary, set, which are also Python collection data types or arrays, a file object, and even custom classes can be iterable if you implement the right protocol. We've seen range many times already, but now we'll look at it in the context of being an iterable. We'll save the other iterables for subsequent videos. The range object. 1. Syntax and basics. The range object is incredibly efficient and easy to use. The syntax is range, start, stop, step. In the above, start is optional. The starting value of the sequence defaults to 0. Stop is required, the end value of the sequence. Crucially, this value is exclusive. It's not included in the sequence. Step is optional. The integer value denoting the difference between numbers defaults to 1. The function returns a range object, which represents a sequence of numbers. For example, range 5 prints range 0 to 5. Range 2 to 5 prints range 2 to 5. Range 1 to 10, 1 prints range 1 to 10. Range 3 to 10, 3 prints range 3 to 10, 3. If you check the type, you'll see it's class range. 2. The power of memory efficiency. This is where range truly shines, especially for scientific computing. Unlike a list which creates and stores every single number in memory immediately, a range object is lazy. It does not generate or store all the numbers at once. Instead, it only stores the 3 pieces of information: start, stop, and step. It calculates the numbers on the fly only when you ask for them, like when you loop over it. The big takeaway? Range takes up almost no memory, even for something massive like range of 10 to the 23. This makes it incredibly useful for generating huge sequences without running out of memory. 3. Properties of an iterable. Since range is an iterable, it has a few key properties. Length. Like any iterable, you can find its length using len. For example, len of range 5 is 5. The sequence is 0, 1, 2, 3, 4. Another one, len of range 3 to 12 to 3 is 3 because the sequence is 3, 6, 9. 12 is excluded. Indexing. The sequence consists of elements and you can access any element using its index. Remember, Python is 0-based. My range equals range 10. My range at 3 is 3. Your range equals range 2 to 10, 3. Your range at 2 is 8. The sequence is 2, 5, 8. Immutability. The range object is immutable. You cannot change an existing range object. Trying my range at 3 equals 4 will throw an error because it's not allowed. If you write my range equals range 20 later, you are not altering the original object. You are creating a completely new range 20 object and reassigning the variable my range to point to it. It's like changing a variable from x equals 5 to x equals 10. The integer 5 itself wasn't changed. 4. Best practices with loops. The most natural and Pythonic way to use range is with a for loop. The for loop is specifically designed to handle this kind of iteration automatically, resulting in much cleaner code. Here are some examples. Simple iteration. For I in range 5, print I. Prints 0 to 4. 5 is excluded. Slicing. Start and stop. For I in range 3 to 5, print I. Prints 3, 4. 5 is excluded. Incrementing with step. For I in range 0 to 10 to 3, print I. Prints 0, 3, 6, 9. Decrementing with negative step. Note start greater than stop is required. For I in range 10 to 0, negative 2, print I. Prints 10, 8, 6, 4, 2. A word of caution on indexing in loops. While you can access the values using an index inside a for loop or a while loop, it's generally not recommended. It defeats the purpose of the clean for loop syntax. Worse, you can run into a common index error. Look at this code snippet. Raw equals range 10 to 15. For I in raw, print raw at I. Raw has values 10, 11, 12, 13, 14. Indices are 0, 1, 2, 3, 4. So raw at 0 is 10, etc. This loop tries to access raw at 10, raw at 11, and so on, which are not valid indices for a sequence of length 5. It throws an index error. My recommendation? Avoid using the range index unless you have a very special specific need. Stick to the clean for I in range syntax. Applications to science problems. Enough theory. Let's see how range helps us in scientific computing. 1. Generating sequences of domain variables. In science, we frequently simulate phenomena where a quantity varies as a function of time, position, temperature, etc. This involves generating a discrete sequence of domain variables. Suppose you want to divide an interval AB into n equal subintervals. Then the width is h equals b minus a over n. The partition points xn are xn equals a plus n times h for n equals 0, 1, 2, n. You can generate these n plus 1 values using range of n plus 1. Assume user enters a equals 0.0, b equals 1.0, and n equals 10 in a, b, n equals input, enter left, right endpoints and number of subintervals, dot split. Then typecast them a equals float a, b equals float b, n equals int n. Again, h equals b minus a over n. Then generate points with range function. For n in range n plus 1, x equals a plus n times h, print x. This would print 0.0, 0.1, 0.2, and so on. Perfect for setting up a discrete simulation. 2. Evaluating a function over a domain. Let's evaluate the function f of x equals x cubed over the domain x in -2 to 2. First, we define our function using double asterisk operator for exponentiation in Python. Define polynom x, return x double asterisk 3. We'll divide the interval -2 to 2 into 10 equally spaced subintervals. The length L equals 2 minus -2 equals 4. N equals 10. The step size dx equals L over n equals 0.4. We use range of n plus 1 to loop through the 11 points. N equals 10, L equals 4, dx equals L over n. Print headers. Print x caret 5 backslash t x cubed caret 7. In the above, the format specifier in the f string caret 5 means center align the value within a field of width 5. Now compute x and f of x values for partition points with range function. For I in range n plus 1, x equals -2 plus I times dx. fx equals polynom x. Print x greater than 5.2f backslash t fx greater than 7.4f. This prints results, right-aligning the numbers and formatting to 2 and 4 decimal places in a field of width 5 and 7, and it gives us a neatly formatted table of x and x cubed values. 3. Calculating hydrogen energy levels. Now let's turn our attention to a fundamental chemistry problem, calculating the discrete energy levels of the hydrogen atom. The energy levels En are given by the Rydberg formula. En equals minus h times c times ryd over n squared, where h is Planck's constant, c is the speed of light, ryd is the Rydberg constant, and n is the principal quantum number. We can define a Python function for this right away. First, we define our constants based on the standard values. H equals 6.626 E-34 joule per second. C equals 2.998 E8 meters per second. RYD equals 10973731.568157 per meter. The function for the hydrogen energy formula is define energy N. En equals minus h times c times ryd over n squared, return En. Let's calculate the energy for n from 1 to 10, so we use range 1 to 11. Print hydrogen energy levels for n equals 1 to 10. For n in range 1 to 11, print n energy of n. This short, clean loop generates the corresponding energy value for each quantum number in the sequence, allowing us to easily analyze the discrete hydrogen spectrum. 4. Calculating quantum states, or the n-squared rule. In quantum mechanics, for a given principal quantum number n, the total number of allowed orbitals, or states, is n squared. The total is the sum over all allowed L, orbital quantum number, and ml, magnetic quantum number, which is equal to n squared. We can use nested for loops with range to prove this is true for any n the user inputs. N equals input, enter principal quantum number. N equals int n. Initialize sum of orbitals, u equals 0. Looping over L. For L in range n, loop over ml. For ml in range negative L to L plus 1, u plus equals 1. Print the result and compare. Print n equals n, sum over L and ml equals u, n squared equals n times n. You'll see the calculated sum u is indeed equal to n squared. The range object-based iteration makes demonstration of these quantum relations straightforward. Wrapping it up, we've covered a lot on the range object today, from its super-efficient memory management to its essential role in iterating through sequences for scientific computation. Range might not be fancy or shiny, but it's an incredibly handy workhorse in computational chemistry and other sciences. That's all for today, folks. We'll see you next time with more exciting topics as we explore other essential iterables in Python.